My name is Birdean Calin from Polytechnic University of Timișoara, Romania, and today I'm going to present you the paper Numerical Analysis of an Inline Connection for Hollow Sections. This paper presents the results of an experimental program of an inline connection for rectangular hollow sections, which stand as a reference for the validation of a finite element method. Nowadays, the design of the building envelopes is more and more challenging than it has ever been. I brought here some examples. Musée de Confluence in Lyon, France. The building should have the shape of a cloud, as the architect imagined it. In the lower part we can see the World Financial Center, glass curtain wall that hangs on two steel trees. At the top we can see the Novartis campus in Basel, Switzerland, that should look like glass blocks stacked together. And in the lower part we can see the Museum of Human Rights in Winnipeg, Canada, which has the shape of a bird that it's closing her wings together. In those two last examples I brought pictures by daylight and by night, so that we can see by night also the structure of the building, not only the envelope. Why I'm bringing the structure in the first plan is that the architectural exposed steel systems became the trademark of a building. As we can see, the glass funnel and its structure in Musée de Confluence in the upper two pictures, and the trees from the World Financial Pavilion in New York. In order to get these shapes, another challenge must be overcome, and that of choosing the right location of the connections and also connection types, in order that the steel groups would be possible to transport and install as economical and efficient as possible. At the top we can see the structure model of the Musée de Confluence in Lyon, and at the bottom we can see how the steel trees in the World Financial Center in New York were split. In order to get those flowing shapes, we have to change this visible connection, the typical one that we can see on the left, into non-visible connection, as we can see on the right, without welding on site, of course, only bolted. For that purpose, an experimental stand was set up to determine the response of an inline connection of two RHS profiles. Each element assembly consists of the RHS 250 x 150 x 8 profile with a support end plate and the connection end plate welded inside the profile. Each element assembly had a cut 150 by 110 as a hand hole for access the M20 grade 10.9 bolted connection, which reduce the capacity of the structural element. A gap of 4 mm exists between the two connection end plates to allow direct contact between the RHS profiles, such that the continuity aspect of the element is provided. A 4-point bending test was used for the load application on the two identical test specimens. The boundary conditions at the supports, as we can see on the right pictures, allowed free rotation of the specimen and as well as free horizontal translations. The joint separation was determined using a 3D optical system based on a digital image correlation technique. Two gauges were defined on the tension side of the specimen, one on each profile. The results are as following. The force displacement curve were recorded for the two specimens, the moment displacement curves, and also another important parameter was the separation between the LHS profiles. Going further, a finite element model was defined to observe the response of the joint and for parametric investigations. The analysis was performed using Abacus software. 3D solid elements were defined as part of the assembly for the LHS profile, connection, end plate, and bolt, respectively. The material properties were considered from the tensile test performed on a specimen extracted from the LHS profile and from the bolts material. A pin and a roller support were defined at the assembly ends, while a displacement of 30 mm was defined using reference points in the point loading position. The connection end plate was connected to the LHS profile using the tie constraint. Supplementary contact interaction are necessary to be defined between the bolts and the end plate and between the two LHS profiles which are in contact. Each part was meshed. The size of the element was approximately 5 mm, allowing two elements on the thickness of the LHS profile. In order to reduce the computation time, the length of the finite element in the longitudinal direction was increased. For the bolts, a preload of 130 kilonewtons was defined in a separate step before the applied load analyzed in a static step. By performing the finite element analysis, the force displacement curve is compared to the one obtained from the experiment, as we can see on the first picture on the left top. The influence of the access hole was also studied, with hole and without hole, and the influence of the preload of the bolts. An important phenomenon shown by the model is the non-uniform distribution of the pressure between the LHS profile as well as the bending in the bolts already developed in the preload stage, as we can see in the middle bottom two pictures. Besides the stress distribution, the rigidity and the maximum capacity of the assembly, the separation of the two LHS profiles is of interest due to the aesthetics considerations, as the connection should never separate to keep the continuous aspect of the element. As I said, the flowing shape. As conclusions, we can say that aesthetic considerations are imposing structural components to be designed in an uncommon way. The study shows a small decrease in the rigidity of the assembly due to the cut in the LHS profile. A small influence is also shown by the preload level due to the distance between the connection end plates. This distance is set such that the LHS profiles to be in contact for a continuous aspect of the joint. A great influence in both rigidity and capacity is assigned to the thickness of the end plate. The end plate thickness, due to its deformation, leads to major bending imposed to the bolts, thus a smaller capacity of the connection. And I would like to thank you very much for your attention.